Alright, so this is the overview on relative motion analysis. So what is the difference between chapter 1 and chapter 2? Usually in the chapter 2 and chapter 3, you will calculate or you will do the analysis on displacement, velocity and acceleration with respect to a fixed point. Meaning that the points that you refer is not moving, it's not in motion. Okay, let's say you calculate the particle from A to B. Okay, so let's say the particle move from A to B. The position here, okay, is fixed position, it's not in motion. Okay, let's say you want to calculate what would be the height here, what would be the horizontal distance, what would be the velocity at position B, what would be the vertical distance, what would be the maximum height, for example. So it is based on a fixed point, meaning that at the position A, the the condition is not in motion. Okay, so in this chapter, you will do the analysis of the velocity of the displacement, velocity, and acceleration, where both points are in motion, meaning that at position A and position B, both positions are in motion. They are in motion. Okay, that's why we call as a relative motion analysis. Okay, so for this example here, in this diagram, you have a fixed position O. Okay, fixed position means that at point O is not in motion. And if you want to calculate or do the analysis of displacement to point A, you just use the symbol of is SA. Okay, the symbol of displacement is S. Okay, and then if you want to measure the displacement from fixed position O to B, then you just put SB. Okay, usually you just put SX, S not X, SY, S not Y. Okay, but for the case of this analysis, we want to determine what would be the displacement between the particle A and particle B. Both particles are in motion. Okay, let's say for examples, I want to do the analysis of displacement of A relative to B, meaning that the displacement of A with respect to point B. Okay, means that I look particle A from point B. So the direction here is point B to A. Okay, displacement of A relative to B. Okay, displacement of A relative to B. Okay, so means that I'm looking from point A, I'm looking point A from point B. Okay, that's why the direction of the vector is from point B to point A. Okay, if I want to measure the displacement of particle B relative to particle A, means that I want to determine the position of point B when looking from point A. So means that point A to point B, or particle A to particle B, which is SB stroke A. Okay, so this is the symbol that we use in relative motion analysis. Okay, so in order to remember the equation, okay, uh, let's say I have a displacement of A relative to B. Okay, means that I want to measure this displacement. So in order to measure displacement, I will use SA here minus with SB. So SA minus with SB. So this displacement A minus with this displacement B. Okay, if you notice that if SA minus with SB, since SA is lesser compared to SB, then you will get negative value. Okay, you get negative value. Why you get negative value? Okay, so because SA is shorter compared to SB, and then you may notice that the direction here is to the left. Okay, that's why we can say that SA minus SB. Okay, and then if SB stroke A, or displacement of B relative to A, is equal to SB minus with SA. Okay, if you want to measure this displacement, means that SB just minus with SA. Okay, then you will get this remaining displacement. Okay, all right. So this is the equation that we can obtain from this diagram. Okay, so during the analysis, in order for you to develop the equation, you just use this kind of equation, okay, to remember. And then for the analysis, I suggest to all of you to use this equation. Okay, means that to remember the equation, you just use this one, and then you rearrange, you will get SA is equal SB plus with SA relative to B. And then here you can rearrange SB is equal to SA plus with SB relative to A. Okay? Because why I say that it's easy to use all the vector in this equation in positive form. Okay, it's easy. So if you use negative form during the analysis, you will get confused. Okay, if the direction of the vector is to the left or to the downwards, it will get negative. So you will confuse with this negative sign in this equation. Okay, let's say the displacement SB is negative. And then if you put into this equation, you will have two negative from the equation and negative from the displacement. So sometimes students get confused when using the equation of this form. Okay, so I suggest to all of you, during the analysis, you just use the positive equation. Okay, the positive form of the equation. Okay, so you don't get confused. All right. So since we know that if we differentiate displacement, we will get velocity. Okay, velocity is equal to ds over dt. So if I differentiate this equation or this equation, I will get velocity. Okay. So if you notice that the form of the equation is the same, just different with the symbol. Okay, let's say you have SB is equal to SA plus SB stroke A, you still get the same equation, but then with different symbol for the velocity. So VB is equal to VA plus VB stroke A. Okay, or you can rearrange into this form, into negative VA here. Alright, so if you notice here, VB is velocity of particle B at an instant, and VA here is velocity of particle A at the same instance, meaning that both velocity B and VA should occur on the same time, at the same time. Okay, VB and VA should, you need to use the velocity B and A at the same time. Okay, at the same instant. And then VB stroke A is velocity of B relative to A. VA stroke B is equal to velocity of A relative to B. Okay. Alright, then you can differentiate the velocity to get acceleration. Okay, you differentiating with respect to time, again give the acceleration. Okay, so AB, acceleration at particle B is equal to acceleration particle A plus acceleration of particle B relative to particle A. Okay, the same things for the negative form equation here. Okay, you can rearrange the equation. Okay, if you notice that the arrangement of the equation is the same, just different with the symbol. Okay. All right. So in this chapter, you will deal with two kind of motion. Okay, in chapter 2, you deal with rectilinear only. Chapter 3, you deal with curvilinear motion only. But for this chapter, you will deal with two type of motion, which is rectilinear and curvilinear motion. Okay, both particle are in motion. Okay, particle A and particle B are in motion. Particle A moving with rectilinear, particle B moving with curvilinear. Okay, so you need to do the analysis of each particle. Okay, with respect to its motion. Okay, rectilinear motion, what would be the analysis? Curvilinear motion, what would be the analysis? Okay, so you have this kind of equation, relative velocity. So VB is equal to VA plus VB stroke A, or VA is equal to VB plus VA stroke B. Okay, or VA stroke B is equal to VA minus VB. Okay. Alright, so rectilinear motion, V is in the direction of motion. Okay, V always in the direction of motion for rectilinear motion. Okay, for a curvilinear motion, V is tangent to the curve and in the direction of motion. Alright, V tangent to the curve in the direction of motion. Okay, so if you deal with vector, okay, you have two common methods of analysis, which is trigonometry or rectangular component method. Okay, from trigonometry, you need to draw the vector in the form of triangle, and then you use a trigonometry method. Okay, so maximum for this method should three vectors only. Okay, for rectangular method, it can be more than three vectors. Okay, if in the analysis you notice that you have more than three vectors, then you need to use rectangular method. Okay, if you have less than three, then you can use trigonometry. Okay, if you notice here, in this equation of velocity, you have VB, you have VA, you have VB stroke A, which is three vector. So means that you can use trigonometry or rectangular component method. It's up to you. Okay, which method that you prefer when doing the analysis. Okay, all right. This one is for relative velocity. Okay, and then we need to go for relative acceleration. Okay, if you notice that the form of the equation is the same, but we just change the symbol into acceleration. Okay, since we have two type of motion, for rectilinear motion, the particle accelerating is in the direction of V. Okay, let's say from point A to point B. Okay, this is the direction of motion, so this is your V. Okay, if your acceleration is in direction of motion or in the direction of V, then this is accelerating. Okay, acceleration. Okay, and if from point A to point B, this is your V, and then this is your A. So this is the decelerating position. Usually we will put here as slowing down. Okay, deceleration. Okay, so this is the terms that represent that A is opposite direction to V. Okay, so you may notice that when you do the analysis or when you have problems in this chapter, you may notice this term. Okay, to represent that either acceleration uh, in the same direction of V or not. Okay, if slowing down or decelerating, this will give you the information that acceleration is in opposite direction to V. Okay, if the particle moving with constant V, then you have zero acceleration. Okay, all right, then we go on acceleration analysis for curvilinear motion. Okay, so velocity of particle is tangent to the curve and in the direction of motion. Okay, all right, so for the acceleration, okay, you need to resolve into two components, normal and tangent. Okay, so let's say This is the path of your particle, and then this is your particle or particle B, let's say. So this is the direction of motion or velocity. Okay, so at this particular position, this particle will have acceleration to tangent and acceleration to normal. Okay, acceleration to normal is equal to v squared over rho, and then acceleration to tangent. Sometime deformation will provide you moving with constant velocity. If particle B moving with constant velocity, then acceleration to tangent equal to 0. Okay, if constant velocity. Okay, let's say for example, it's mentioned that particle B is slowing down. Slowing down means that your AT is opposite to V. So this is your AT. Okay, acceleration to tangent. So you need for AT, it will provide the information will be provided in the question. Okay. Okay, please remember for normal components, the direction to the center of rotation. Okay, or inward to the curve. Okay, in the positive and axis. All right. Okay, so for the tangential component, analysis similar to rectilinear motion. So particle accelerating AT in the direction of V, particle decelerating AT opposite to the direction of V. So particle moving with constant V, AT equal to 0. All right. So for this acceleration analysis, you have two common method, either trigonometry or rectangular component. Okay. So usually for acceleration, mostly we use rectangular component. Okay, usually. Okay, because in acceleration you have more than usually you have more than 3 vectors. Okay, so it's preferred to use a rectangular component method. All right. So this is relative the analysis that you need to do. Okay, if you use trigonometry, you need to form the vector into a triangle form. Okay, so like I mentioned, if you have a velocity of b relative to a, in order to remember the equation, I will use vb minus va. Okay, so in the analysis, what I will do, I will rearrange the equation into positive form. I will get vb is equal to va plus vb stroke a. Okay, why it is important? When you draw the vector, it's easy. Okay, it's easy to draw this vector into a trigonometry or into a triangle form. Okay, let's say you have VA plus VB stroke A is equal to VB. Okay, meaning that VA from a starting point VA plus with VB stroke A is equal to VB. Okay, is equal to this vector. Okay, because you use a positive form. Let's say if you want to use this form, this negative VA will change this direction. So instead of this direction, you need to change the direction into that direction. Okay, due to this negative equation here. So that's why I mentioned to you in the analysis is preferable to use this positive form equation. Okay. Okay, so this is the sign rule. Basically, this sign rule is similar if you read, because this sign rule is actually a ratio, okay, between the vector and the angle. So you can use sine beta over VB is equal to sine alpha over VA is equal to sine gamma over VB, so A. So it's the same, okay, it's the same things. And for the cosine rule, okay, I believe everyone familiar with this equation. Okay, you have a vector. Let's say you want to determine this vector. So you will use VB and VA along with this angle. Okay, the angle between the known vectors. All right, so this one is for trigonometry equation. trigonometry methods. Okay. Uh, if you notice here, you have a VB, VA, and VB through A. Then you have only three vectors. Then you can form the triangle. Okay. From that triangle, you can use sine rule and cosine rule. Alright. Any questions so far? Ada soalan ke? Okay. So alright. So that's all for the information and the concept of this chapter. Okay. So it's just a simple concept. Alright. So then we go on the example 4.1. Okay. For the instance shown, particle A is moving with a velocity of 72 kilometer per hour. Okay, and particle B is taking a 150 meter radius of curvature band with velocity of 54 kilometer per hour. Determine the velocity of B relative to A. Okay, so the question asks you to determine velocity of B relative to A. Okay, velocity of at position B of particle B when looking from point A, when observed from point A. Okay, so like I mentioned, in order to remember the equation, I will use VB minus VA. And then after that, I will rearrange this equation into positive form. I will get VB is equal to VA plus VB so A. Okay, so then we need to get the information from the question. So question A is moving with a velocity. So we know that question A is moving to the left, okay, with a velocity of 72 kilometer per hour. So you need to change to meter per second. Okay, 72 over 3.6. Okay, then you get a meter per second. Okay, and then we know that particle A is actually moving with rectilinear motion. Okay, moving with a straight line motion. Okay, to the left. All right, and then particle B is taking a curvature band with a velocity of 54 kilometer per hour. So V here is 54 over 3.6 to change with meter per second. And then we know that at this position is moved with curvilinear motion. Okay, it move with curvilinear motion. Okay, here is actually 20, here is 15. All right. So then here you have the information. So let's put the information in the table first, okay, to get yeah, usually for this chapter, I would suggest student to use to put the information in the table. Okay, so here is magnitude, all right, and here is direction. Okay, which means that the angle. Okay, the direction is actually the angle. All right, then I will put the information here is VB. Okay, then I put the information VA. Okay, then I put here is VB. Sorry. Okay, so VB is actually 15. All right, and then you need to determine what would be the angle. What would be the angle here? Okay, we know that from the this is tangent, so we know here is 90 degree. All right, then you can determine the angle. Okay, let's say if I make it so this is position B given with the center of the rotation. So this is the center of rotation provided in the question, 30 degree. And then this is the curve. So here, tangent to the curve is actually your V. Yes. Okay, tangent to the curve is your V. Okay, so we know that here is 90 degree. So if you draw the line here, okay, here you get 90, here you get 60. So from here, you know that here is actually 60 degree. Okay, because here is 30. All right, so for VB, here is the direction here is 60 degree. Okay, and then VA is 20, and the direction here is to the left. Okay, and then VB slash A is unknown, and also the direction you don't know. You don't know the direction of VB slash A. So this is uh, the the information, the unknown that you need to determine. All right. Okay, so since here we have only VB, VA, and VB slash A, then you can use trigonometry method. Okay, let's say I use trigonometry method first. Okay, meaning that I need to draw the uh, triangle. Okay, so the start point. Okay, start the start point is here. So start point VA to the left, which is 20, and then I don't know what would be the direction. So from the start to the end should be VB. Okay, from the start to the end should be VB. So I know VB 15. Okay, and then uh, VA plus VB slash A is equal to VB. Okay, so VA plus with VB slash A is equal to VB. So you will notice that the flow here, VA plus with VB slash A is equal to VB. Okay, the direction of the vector VA plus with VB slash A is equal to VB. Okay, here you know the angle 60 degree. All right, so then you can determine VB slash A squared is equal to VA squared plus VB squared is minus 2VA VB cos 60 degree. Okay, so VB slash A is equal to square root VA is 20 squared plus with 15 squared minus 2 times with 20, 15 cos 60. All right, then you can get VB slash A in meter per second. Okay, any question? Soalan? Ada soalan ke? All right, then you can get the value of VB slash A here. Okay, so from the books, the value is 18.03. Okay, then you can use sine rule to determine what would be the angle here, the angle from the horizontal axis. So okay, usually for the direction, we will use the angle by referring to the horizontal axis. So here is your horizontal axis, and then this should be your angle. Okay, so sine theta opposite to the vector here is 15. is equal to sine 60 over 18.03. Then theta is equal to sine inverse 1815 times with sine 60 over 18.03. Then you can get your theta. So 46.1. Okay, so your final answer should be in this form, which is VB slash A is equal to 18.03 with the angle of 46.1 degree. Okay, any question? Ada soalan ke? Okay. So you may notice that if you use a positive form equation, okay, if you use the positive form equation, you just directly use the direction here, the direction of this given in the question. Okay, if you use this negative form, means that this VA here, instead of direction to the left, when you draw the triangle, it should be to the right. Okay, due to this negative sign here. Your VA should change the direction. Instead of moving to the left, it should move to the right. Okay, if I take the example from the books, okay, I will show to you. Okay, so you may accept that this is the difference if you use a positive form equation and this equation. You may notice that the direction of VA is opposite to the actual velocity. This is due to the negative sign in the equation. Okay, so from the question, the velocity is actually to the left, but then when you draw the trigonometry triangle, the VA is to the right. Okay, due to this negative sign in the equation. Okay, so I suggest to all of you just use the positive form equation here, so that you can directly use all the direction provided in the question. Okay, all right, so this one is the same things. Okay, so for this example, I want to show to you on using the rectangular component. Okay, the same example, but with another method, which is rectangular component method. Okay, uh, first you need to draw a table. Okay, to put all the information that you have. Okay, from the question. Okay, you know that VB slash A is equal to VB minus VA, and then rearrange the equation. VB is equal to VA plus VB, so A. Okay, then you put the information according to this equation. So here you have magnitude, okay, and then you have here is the angle or direction, okay. So here is VB, okay, here is VA. All right, for rectangular component, what you will do is you will resolve the force or the vector into x and y axis, okay, into x and y axis. So since we know that in this question, this is unknown, okay, VB, so A is actually unknown. We don't know what would be the magnitude and what would be the direction also. So what we do, we will put VB through A in terms of x-axis and then VB through A in terms of y-axis. Okay, then we will fill this table with the information that we get from the question. So VB is 15. And the angle here is 60 degree. All right, and then VA is actually 20 and moving to the left. Okay, for this value is unknown. We don't know what would be this VB through A along X. So we just put in term of unknown, and then the direction, we assume the direction. We made the assumption for the direction. Okay, so I just assume that VB through A along X is just to the right. Okay, this is we assume. Okay, we assume the direction. All right, same goes to VBAY. We assume also upward. Okay, we will get the correct direction after we do the calculation. Okay, and then here is VBAY. Okay. So now what you need to do, you just use a horizontal analysis, which is x-axis, where you say that to the right is positive. Okay. All right. So this is the equation that I will use during the analysis. Okay. So VB is equal to VA plus VB through A. So since I do the analysis on the x-axis, so I put here is VBX, VAX, and here is VB through AX. Okay. So what would be my VBX? 15 cos 60 to the left. So negative 15 cos 60. Okay, because if you resolve this vector, it will directed to the left, so negative, because we assume that to the right is positive. Okay, because we assume here to the right is positive. So VAX is 20 to the left, negative 20, plus VBAX is actually unknown. So your VBAX is equal to 20 minus negative 15 cos 60 degree. Then you get your VBAX is meter per second. Okay, 12.5. All right, then you go on vertical component, vertical, which is a y-axis. All right, upward positive, we assume outward positive. So the same things, we will use the general equation in y-axis. So we have VB equal to VA plus with VB through A. Since we do on y-axis, so VBY, VAY, and VB through AY. Okay. So we substitute based on this table. VB is if we resolve 15 to y-axis, we will get negative 15 sine with 60 degree is equal to VAY. VAY only along horizontal component, so we don't have VAY. So VAY is actually 0. Okay, and then plus with VBAY because we made the assumption here upward, so positive. So VBAY is equal to negative 15 sine 60 degree is equal to negative 13 meter per second. So you may notice here, VBAY, you obtain negative value. You obtain negative, meaning that the assumption that you made here is wrong. So the correct direction of VBAY is actually downward. So here is 13 meter per second downward. And then for VBAX, you obtain positive magnitude, meaning that the assumption that you made here is correct. Okay. So then next what you need to do is you need to draw the VBAX. Okay. So you know that VBAX is actually to the right and VBAY is actually downward. So in order to get the total VBA, so you draw the vector. So VBAX is to the right with 12.5, and then VBAY is downward, which is VBAY is 13 downward, and then your total VBA should be here. Okay, VBA. So this is your angle. Okay, theta. So VBA is equal to VBAX squared plus with VBAY squared. Okay, so this is the usual step, the common step for rectangular component. Okay, you find the vector along x and vector along y, and then you use this analysis to calculate the total magnitude and also the direction. Okay, so VBA is equal to 12.5 squared plus with 13 squared. Okay, and then the theta is equal to tangent inverse 13 over 12.5. Then you can get your theta. Alright, so what would be your theta? Any questions so far? Ada soalan ke? Okay, so usually for velocity, we will have three vector, which is VB, VB, VE, and VB through A. So you can choose either you want to use trigonometry or rectangular. Okay. Alright, so if you don't have a question, so let's have a look to this example here. Okay, for the instance shown, particle A is moving with a velocity of 30 meter per second, while particle B is taking a 150 meter radius of curvature band with a velocity VB. If magnitude of the velocity of B relative to A is found to be 40 meter per second, determine the magnitude of VB and the direction of VB through A. Okay, so the question just provide the velocity of B relative to A, which is 40 meter per second. Now you need to determine what would be VB and also the direction, the angle. You know the magnitude of VB through A, but you don't know what would be the direction or the angle of VB through A. Okay. Okay, you may notice that in the question, usually you need for this velocity, you have two unknowns that you need to determine. Okay, for question 4.1, you need to determine the magnitude of VBA Okay, magnitude and direction. Magnitude and direction. Okay, you have two unknown here that you need to determine. Because if you use a rectangular component, you have only two equations that you can develop. So two equation, you can solve two unknowns. For this case here, 4.2, your unknown come from VB and the angle of VB through A. Okay, because the magnitude of VB through A already provided in the question, 40 meter per second. Okay, so for this case, it's actually the same as a previous example. So you know that A is rectilinear motion, and then B is actually curvilinear motion. Okay, and then you know VB through A is equal to VB minus VA. So rearrange the equation. VB is equal to VA plus VB through A. Right? Then we put in the table. Okay, put in the table magnitude and direction. Okay, then you have here is VB, then here is VA, then here is VB through A. Okay, so here is VB is 1560 degree. Sorry, VB is unknown. With 60 degree. VA is to the left. Given here is 30. Sorry, magnitude 30 to the left, and then VB so A is the font 40, and then direction is unknown. Okay, so then you can draw the triangle since you have only three vectors. So the start point here, start is VA, and then from the start to the end should be VB, because VA plus VB through A is equal to VB. So from the start to the end is actually your VB. Okay, this one is N. So from VA, from the start, move to VA and then move to VB through A. Okay, VA plus VB through A is equal to VB. Okay, so you have this kind of triangle, then you have here is 40, you have here is VA is 30. Okay, VA here is 30. VB is unknown. Alright, so means here you need to find what would be the theta here, what would be the alpha. So you can use a sine theta. Sorry, find sine alpha first. Sine alpha over VA is equal to sine 60 over VB. Sorry. Okay. So this is only the unknown that you don't know. So alpha is equal to sine inverse VA sine 60 over VB. Sorry. Okay. And then you can determine what be alpha. So you know that in one triangle, you can get theta is equal to 180 minus with 60 degree minus with alpha. Then you can get theta. Okay, the angle of VB through A is theta. Okay, so from the theta, then you can determine VB. Okay, sine theta VB is equal to sine 60 VB through A. Okay, then you can solve for VB. Okay, or you can use a rectangular component. Okay, it's up to you. It's up to you. For rectangular component, okay, for the rectangular component, you just need to since from this triangle, okay, let's say you have here is magnitude, and then here is direction. Okay, here is VB, here is VA, and then here is VB stroke A. Okay, here is unknown VB with the direction 60 degree, and then VA is 30 to the left. You know here is 40. Okay, in order to use rectangular component, you need to assume the direction. Okay, rectangular method, you need to assume the direction of this one. Assume the direction. Okay, in order to assume the direction, you can refer to this triangle. Okay, you can refer to this triangle to assume the direction. So for this case, you know that VB stroke A should be in this direction, so you can put here as this one, theta. So in the question, in the x and y axis, you have 40 cos theta and 40 sin theta. Okay, where the unknown here now is theta. You will get the correct direction after you do the calculation. Okay, any questions so far? Ada soalan ke? Okay, if you don't have a question, we will take a break for 5 minutes. So I think we will continue at 9:30 a.m. Okay, for 5 minutes. Okay, guys, so let's continue to example 4.4. Okay, okay, I hope everyone already here now. All right, so for this example 4.4 is actually for the acceleration analysis. Okay, so this example is for acceleration analysis, where you may notice that you have the information of acceleration. And the instance shown, particle A is moving with velocity of 20 meter per second with an acceleration of 3 meter per second squared. Okay, and then and particle B is taking a 150 meter radius of curvature band with a velocity of 15 meter per second and slowing down at a rate of 2 meter per second squared. Okay, and then you need to determine the acceleration of B relative to A. Okay, so here you have the information, velocity A 20, VA is equal to 20 meter per second, and acceleration A is equal to 3 meter per second squared. Okay, so for A also rectilinear motion. Okay, you need to know what type of motion that the particle uh, are in, and B is velocity of B is 15, VB 15, and it's already mentioned here, slowing down. Okay, slowing down means that decelerating. Okay, so means the acceleration is opposite to velocity. Okay, acceleration is opposite to velocity. So this is your VB. So your acceleration AB should opposite to VB. Okay, in opposite direction. So this is your AB, which is 2 meter per second squared. Okay, due to the slowing down, because I already mentioned here, slowing down. Okay, so the question asks you determines the acceleration of B relative to A So the same things, acceleration of B relative to A is equal to acceleration of B minus acceleration of A. Okay, rearrange the equation, you get acceleration of B is equal to acceleration of A minus acceleration of B relative to A. Sorry, plus. Okay, so now in this case, for the acceleration, you need to consider the acceleration to normal and acceleration to tangent. Okay, so the particle that move in curvilinear, okay, curvilinear will have acceleration to tangent and acceleration to normal. And the curvilinear motion only happen for particle B. For particle B. All right. So since you need to determine what would be your AT and AN, all right. So you need to substitute AT and AN into this equation. Okay. Curvilinear into particle B. Particle B move with curvilinear. So your equation will look like acceleration B to tangent plus with acceleration B to normal is equal to acceleration particle A plus with acceleration B relative to A. So now your equation contain four vectors. Okay, four vectors. Acceleration B to tangent and acceleration B to normal. So here, okay. So then you need to draw the axis of tangent and the axis of normal. So here, follow the direction of motion is your tangent axis, right? And then follow the inward to the curvature, which is on the rotation, okay, on the rotation direction, which is your n. Okay, this is the center of rotation. Okay, center of rotation. All right. So center to the rotation is your n. Okay, n axis. All right. So now what you need to do here. Okay. So you need to resolve the acceleration 2 meter per second. Okay. So given here is AB. AB is along tangent. Okay, along the tangent line. Okay. So means that the provided information here is for tangent. Okay, the information that provided slowing down here is for ABT. Okay, so I put into the table first. Here is magnitude. Here is direction. Here is acceleration B to tangent axis. Acceleration B to normal. Acceleration A. And then here is, since here you have four vectors, so you need to use rectangular method. Okay, rectangular component method. So we can directly put acceleration B to X axis, acceleration B to Y axis. Alright. So along tangent here, you already given with the information slowing down, which is opposite to the velocity direction. So you have here is actually acceleration B to tangent, which is 2 meter per second squared with the direction opposite to the velocity, 60 degree. Okay. So acceleration B to normal, which is here, is equal to VB squared over rho. So VB is given to you 15 squared over 150 meter. Okay, so it's equal to 1.5 meter per second square. Okay, meter per second square. So the magnitude here is 1.5. So you need to determine the angle here from the horizontal axis. So this is the angle. So this angle is actually the same as this angle. So here is 30 degree. Okay. So now you finish with you're done with section particle B, and then go on particle A. Particle A is just 3 meter per second squared here, and the direction is to the left. Okay. And then here is unknown x. So just assume I just made the assumption to the right. Okay, I just made the assume here, and then outward for y, and then a b a y. Okay, so you already complete this table. So what we can do now is just find the horizontal and vertical components. So along horizontal, where I assume that to the right is positive. Okay, based on this equation, okay, which means I have here is acceleration B to tangent plus with acceleration B to normal is equal to acceleration A plus with acceleration B relative to A. Since I do on x-axis, so I can put the formula x, 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 and x. Okay. So acceleration B to tangent along x-axis. So this one along x-axis is 2 cos 60. Okay, plus with this one 1.5 cos 30 equal to this one negative 3 plus with acceleration B relative to A along x. Okay, so acceleration B relative to A along x is equal to 5.3 meter per second squared. So you obtain positive magnitudes, meaning that the assumption that you made here is correct. So it's actually to the right, correct. Okay, the assumption that you made here is correct. Okay, then we go on vertical component, vertical upward positive y-axis. So we still based on the general equation, which is acceleration of B to tangent plus with acceleration of B to normal is equal to acceleration of A plus with acceleration of B relative to A. Okay, so since we do on the y-axis, so you just put y here, right? Okay, acceleration of B to tangent along y is 2 sine 60 plus with this one 1 point, this not plus, it should be minus since it's below the y-axis, minus with 1.5 sine 30 equal to, so for this case, you don't have acceleration of A along y, so 0, plus with acceleration of B relative to A along y. Okay, and then here you can solve this equation. You get acceleration of B relative to A along y is equal to 0.98. You obtain the positive magnitude also, meaning that the assumption that you made here is correct. So which means that upward. Okay. So then, since you do on you use a rectangular component method, so means that you need to use the form of Pythagoras theorem equation, okay, to find the magnitude and also to find the angle. Okay, so then here is you have here is acceleration of B relative to A x-axis 5.03, sorry, 5.3 meter per second squared, and then you have here is upward acceleration of P relative to AY, which is 0.98 meter per second squared. And then this would be your acceleration of B relative to A with the angle here. Okay, so acceleration of B relative to A is equal to acceleration of B relative to AX squared plus with acceleration of B relative to AY squared. So here you have a 5.3 squared plus with 0.98 squared. Then you get your uh, acceleration of B relative to A. Okay, and then for the theta is equal to tangent inverse acceleration of B relative to AY, acceleration of B relative to AX. Okay, then you get your direction. Okay, 0.98 over 5.3. Okay, so your final answer should be in the form of magnitude along with the direction theta. Okay, any question so far? Ada soalan ke?
No, sir.
Yes? No, no, no question.
No question.
Okay. Alright, so this is for example 4.4. Okay, so there is example 4.5 here, which is similar to example 4.4, but then it's mentioned that you have here is constant velocity. Okay, means that particle B is moving with constant velocity. So means that you don't have, since velocity is tangent to the curve, is tangent to the curve. Okay, and this velocity is constant. So meaning that your acceleration B to tangent is equal to 0. Okay, because velocity is tangent to the curve and acceleration B to tangent is actually 0. You still have acceleration B to normal, which is VB squared over rho. Okay, you still have this equation. Okay, so if you want to solve this example, so you just put this example 4.4 here, this ABT here is actually 0 for example 4.5 because constant velocity. Okay, so in your equation, you don't have ABT for example 4.5. Okay, due to the constant velocity. Okay, so your equation will looks like ABN is equal to AA plus with acceleration of B relative to A. Okay, you have this only these vectors in your equation. All right, so we still have um, okay, let's do this one exercise, which is exercise 4.1 before we end this class. Okay, so here you have the figures shows the plan view of jet A and jet B flying on the same latitude. Okay, the same planes mean to show the same planes means that it's on 2D. Okay, two-dimensional. So you just on X and Y axis. Okay, you have two-dimensional space. All right. So jet A is traveling straight. Okay, so you know from the question, you know that this one is rectilinear. Okay, traveling straight with constant velocity, constant velocity. So you have another information, constant velocity. You know that acceleration A is 0. Okay, and then while jet B is flying around the curve, so around the curve is actually curvilinear. With the velocity of 540 km per hour and decelerating at a rate of 10 meter per second. So decelerating means that opposite to the direction of motion. So this is your direction of motion, down vertically downwards. So vertically upward is your acceleration B. I can say acceleration B to tangent because V is tangent to the curve. So decelerating here is 10 meter per second squared. Okay, for the instance shown, okay, means that A and B occur on the same at the same time. Determines the velocity of jet B as observed by the pilot on jet A. So meaning that the velocity of jet B relative to jet A, velocity of jet B relative to jet A, VB minus VA. And then you need to determine the acceleration of jet B as observed by the pilot on jet A. The same things, acceleration of B relative to A is equal to acceleration of B minus acceleration of A. All right. So we go on the first question. Okay, question A. Okay, I rearrange this equation. I will get a VB is equal to VA plus VB stroke A. Okay. Here is I need to change the here. So 720 over 3.6. Okay, here is a 20 to 200 meter per second. Here is over 3.6 and get 150 meter per second. Okay, so now let's put in the table the information that we have. So here is magnitude and here is direction. Okay, so just directly put information VB. Here is VA. Okay, here is VB. So okay. Okay, so for this case, I want to use a rectangular component. So I just use VBAY. Okay. So VB is the magnitude is 150. And then the direction is vertically downward. VA is 200 and the direction is to the left. VBAX is unknown, and I just made the assumption to the right, assume, and VBAY also, I don't know, so I made the assumption upward. Okay, so here I just made horizontal and vertical. So horizontal to the right positive, x-axis. So I bring this equation into x-axis. Okay. Okay, so VBX. So we don't have VBX along. We don't have VBX. So here is 0. VBA negative 200 because it's to the left, and then plus with VBAX. So VBAX is equal to positive 200 meter per second. So I obtain here is positive magnitudes, meaning the assumption that I made here is correct. So to the right. Okay, along vertical, upward positive, y axis. So my equation is V by, the same thing. I used the general equation V by VAY plus VB AY. Alright, so I just substitute the value from the table. So VBY is negative 150, okay, from this table. And then VA is 0 plus VBAY. So from this calculation, I obtain VBAY is negative 150 meter per second, means that the assumption that I made here is wrong. So it's actually 150 meter per second downward. So downward. Okay. So then I just use the Pythagoras method. So this one is VBAX 200, and then here is VBAY 150. Right? Then here is the direction always from the horizontal component. This one is your VBA. Okay, so VBA is equal to 200 squared plus V 150 squared. Then you get here is 250 meter per second. And then theta is equal to tangent inverse 150 over 200. Then you get your direction. Okay, this direction theta. Alright, so this is for question A. Okay, you just use the equation here and put the information. And since I use a rectangular component, so I just put into axis x and y, and then I assume the direction. Okay, but after I do the calculation, I will check either my assumption correct or not, and then I draw this form to obtain magnitude and direction. Okay. Okay, then I go on question B. Okay, so question B is actually acceleration of B relative to A is equal to acceleration of B minus acceleration of A. Okay, so acceleration of B is equal to acceleration of A plus with acceleration of B relative to A. Okay, so since you know that A is rectilinear and B is curvilinear. Okay, so curvilinear. So here is actually curvilinear curve. So you have here is acceleration of B to tangent and acceleration of B to normal. Rectilinear, only one component of acceleration. Okay, because it's straight line, so you have only one component of acceleration. Alright, so your equation will look like this. Okay, acceleration B to tangent plus acceleration of B to normal is equal to acceleration of A plus acceleration of B relative to A. So then you draw table and put all the information that you can gain from the question. Okay, so here is magnitude, here is direction. Okay, so you put everything in the table, acceleration of B to tangent, acceleration of B to normal, here is acceleration of A. Since I use a rectangular component, so I need to put into form for relative acceleration y. Okay. All right. So for this case, it's already mentioned that the particle B is decelerating at the rate of 10 meter per second, means opposite direction to V. So this is your ABT. Okay, 10 meter per second upward. Okay, vertically upwards. And then 90 degree to the tangent is normal, which is this is the center of rotation towards the center of rotation inward to the curve is normal. Okay, toward the center of rotation and inward to the curve is your normal axis. Okay, so your acceleration of B to normal is equal to VB squared over rho. So your VB is 150 squared over rho 1000. Okay, so 1000. So you need to calculate what would be 150 squared over 1000. Okay, so here is 22.5. 22.5. And then direction to the right. Okay, and then acceleration A. Okay, jet A is travel constant velocity. So constant velocity means that acceleration A equal to 0. Okay, so 0. Okay, no direction. And then acceleration B A to X. I just made the assumption. Okay, to the right, and acceleration B A to Y upward. Okay, and then along horizontal component. Okay, horizontal to the right positive x axis. So my equation is acceleration of B to tangent plus acceleration of B to normal is equal to acceleration of A plus acceleration of B relative to A. So I put it in x axis plus with acceleration of B to x plus acceleration of B relative to A x. Okay, so acceleration of B to tangent always y axis. So here is 0 plus with acceleration of B to normal is to the right 22.5. Acceleration of A to X is 0 plus with acceleration of B relative to AX. So acceleration of B relative to AX is equal to 22.5 meter per second squared. I obtain positive magnitude here, meaning my assumption here is correct. Okay, and then I do on vertical component the same things, upward positive y axis, acceleration of B tangent y plus acceleration of B normal y equal to acceleration of A y plus acceleration of B relative to AY. Okay, so acceleration of B to tangent upward 10 plus with acceleration of B to normal always on the horizontal component, so 0. Acceleration of A is actually 0, and then you have acceleration of B relative to AY. So acceleration of B relative to AY is equal to 10 meter per second squared, which means that you obtain positive magnitude, meaning your assumption is correct. So the assumption that you made here is correct. So then what you need to do, you just put in the form here. So this one is acceleration of B A to Y, and here is acceleration of B A to X. All right, and then you need to determine what would be the acceleration of B A and theta here. So acceleration of B A is equal to acceleration of B A to X squared plus with acceleration of B A to Y squared, and then you get your magnitude. Okay.
Sir,
Yes.
so the answer given is wrong, right, for the angle?
Yes, correct. This angle is wrong. It should be this direction. Okay. So theta is equal to tangent inverse acceleration of B A to Y over acceleration of B A to X. Then you get your angle and magnitude. Okay, any question so far?
No, sir.